Okay, today we're going to look at 3.6, which is dealing with polynomials and rational functions. So a rational function comes in the form of p of x over q of x, where p of x and q of x are polynomials. So polynomials of any degree. So if we look at this first example, f of x equals 1 over x. The numerator is a polynomial. It's of degree 0. And the denominator is a polynomial of degree 1. So we really have like 1x to the 0 over x to the 1. We just don't usually write any of those things. So the most basic of these is 1 over x. It's like our parent function we've used for a long time. And in this picture, we have a picture of x, or 1 over x. And you'll notice all of these, f of x goes to infinity as x goes to 0 from the positive side, and f of x goes to infinity as f of x goes to 0 as x goes to infinity. So that's talking about end behavior, which we'll talk about a little bit later. But we'll look at that. We'll look at that again later. So if we get to our first example, f of x equals 2 over x minus 3. So with this one, since it's so similar to 1 over x, we're just going to use 1 over x as our example. So f of x, if I factor out the 2, I'm left with 1 over x minus 3. So in that denominator, we can't plug in a 3 because it'd be 0. So that tells us that our vertical asymptote is at 3. Okay. And the 2 is really just a vertical stretch factor, which we're not going to be able to see really on my graph because this is not a super accurate graph. So I have a horizontal asymptote, which again, we'll talk about those. And so this is just like 1 over x, except a little bit, has a little bit of a vertical stretch, and it's shifted over 3 units. Okay, so in this one, f of x equals 3x plus 5 over x plus 2. This is similar to the last one. We can use the idea of 1 over x to graph this. And to do that, we're going to use polynomial long division, which everybody loves. So 3x plus 5 divided by x plus 2. And so what this will do is put this in a form that's more like 1 over x. So if we go through this division, 3x divided by x is 3. Multiply it through, flip the sign. 3 times 2 is 6, and then you flip the sign. This is a remainder of negative 1. So if I rewrite this whole thing, f of x equals 3 minus 1 over x plus 2. So what this shows is that we have a vertical shift of 3, a vertical asymptote of negative 2, and this negative sign here means our graph is reflected in the x direction. So I'm going to first put the asymptote at negative 2. And 1 over x usually has an asymptote at 0, but this has a vertical shift of 3, so this will shift that asymptote to 3. And if we, let's go back and look at this one. So if we look at the shape of 1 over x on the graph, you can see that it's in quadrants 1, which is here, and 3, which is here. So if you have a negative sign out front, it's going to flip these. So we'll instead, in our example, have a graph drawn in 2 and 4. So I would have, again, this graph's not super accurate, but it'll be right there and right there, something like that. Okay, so let's go to another example. So this is sketching graphs of rational functions. This is more of what this section's about. in this little box, this is in your textbook, I just cut and paste it here. So you factor, you're going to find your intercepts, vertical asymptotes, horizontal asymptotes, and then you'll sketch. So these are sort of long problems because there's so many steps here. And the first thing I'm going to work with are the idea of horizontal asymptotes. So for this, I'm really talking about horizontals for now. And I have 3 examples. So these are going to be 3 different types of horizontal asymptotes. I actually see a little mistake in here, so I'm going to adjust one of them. Make this 4. Okay, so let's just zoom in on this first one and look at it. So we're trying to find the horizontal asymptote. So an asymptote is it's a value on a graph. So horizontal asymptote is going to be a y equals some number value on a graph where the function ultimately settles around it. So if we go back to our first example, just look at this 1 over x, you can see that the asymptote value, the horizontal asymptote, is at y equals 0. And that's because if you look at this line here on the right, as x goes towards infinity, gets really big, this function is going to settle around 0. Same thing on the left. As x goes in the negative direction towards negative infinity, the graph is going to settle around the horizontal asymptote. Now, in some functions, it can cross the horizontal asymptote. You can't cross vertical asymptotes, but functions do cross horizontals. But at infinity, they will settle around that value. So if I go back to my example, purely from the algebraic representation of this, it's a little different. So what I see here is a x squared and x to the third. So what this tells me is that the horizontal asymptote, I'm going to start abbreviating this because it's too much to write. The horizontal asymptote is going to be y equals 0. And that's going to be when the degree of the numerator is less than degree of denominator. Okay, so if that happens, if you look at that, and we're just looking at the leading terms, we don't have to look at anything else. So the highest, the term with the highest power in each spot is what we focus on. So if you have a degree that is less in the numerator, it's going to be y equals 0. So if you have this example, and actually let's go back here. This is just to reference the 1 over x graph again. So in that last one we had, or in the very first example, we had f of x equals 1 over x. That has an asymptote of y equals 0, horizontal. And that's again because the degree of the numerator is 0 and the degree of the denominator is 1. So that also holds for that parent function. In the next example, we have x to the 4th plus 3 divided by 3x to the 4th minus 2. So the degree of the numerator and the denominator are the same. So when those are the same, we take the ratio of the coefficients of those terms. So that's 1x to the 4th and 3x to the 4th. So the horizontal asymptote is at 1/3. So you just divide the coefficients of the leading terms. So this is when the degrees are the same. Okay, so you just divide the coefficients. Okay, for our last example, this is, you can see it's x to the fourth plus 2 and x to the third minus 5 in the denominator. So for that, um, these degrees are different and it's higher in the numerator. So if this happens, then there is no horizontal asymptote. Okay, so when the degree, let's see if I can do a little copy paste. So when the degree is higher in the numerator, then you have no horizontal asymptote. Okay, so I'm going to adjust that just so it's here. So when the degree of the is, sorry to do this on this video, is higher. Okay, so if I back up on this, those are the three cases. And so you have an asymptote value of y equals 0 if the degree is lower in the numerator. You have the ratio of the leading terms when the degrees are the same. And there is no horizontal asymptote when the degree is higher in the numerator. And for that other, for example 3, that actually means something else. In that case, it's a slant asymptote for that problem, but we'll look at that later. Okay, in this example, we're going to go ahead and graph this, and this is kind of a long process. So I'm going to go through each thing and I'll number each step as we do it. So the first thing you want to do is factor. So we are going to factor both the numerator and denominator. So in the numerator, that will factor to 2x minus 1 times x plus 4. And in the denominator, we'll have x plus 2 and x minus 1. Okay, so that's going to make it easier for us later because we can just take a lot from that. Okay, 2, we are going to find the x-intercepts. So the x-intercepts are found from the numerator. So that they are 2x minus 1 equals 0 and x plus 4 equals 0. So the x-intercepts are 1/2 and x equals negative 4. Third thing is going to be the y-intercepts, or intercept. There's only one. Okay, so the only thing you do with that is find, let's name this function p of x. So p of 0. So what do you get if you plug a 0 into this? Sorry, it was already named f of x, so I'll adjust that. So if we plug in a 0, it's easiest to do that with the original function at the top. We would just get negative 4 over negative 2, or 2. So the intercept is 2. The vertical asymptotes, these are taken from the denominator. So we'd have x plus 2 equals 0 and x minus 1 equals 0, and then we solve those. So x equals negative 2 and x equals 1. And finally, the horizontal asymptotes. So the horizontal asymptotes, if we look at this original function at the very top, we are looking at, it's a squared function in the numerator, squared function in the denominator. So we just take the ratio of the terms because the degrees are the same. So the horizontal asymptote is 2 over 1, or 2. I'm going to move some of this a little bit. So now let's graph this. Okay, so I'm going to start with the horizontal asymptotes and the vertical asymptotes. So on my graph, I will have a horizontal asymptote of y equals 2. So I'm just putting that in. And then this one has two vertical asymptotes, one at -2 and one at 1. So this graph is this, we have 6 different sections in this graph. So this one is going to be a little bit of work to work with. The x-intercepts are 1/2 and -4. So we're going to have one here, and we'll have one at -4, which is somewhere out here. All right, so the y-intercept is 2, so we'll have a dot here too. And now we have to work with the what's it doing near the asymptote sort of thing. So for that, let me zoom out a little bit. What we have to do is take our original function. So I'm going to rectangle around, not the original, this one. This is going to be the easiest form to check around the asymptotes. So we have to plug in numbers close to the asymptote value, but not over, or the actual value. So let's look at x equals 1. So that's one of the vertical asymptotes. So on the right side of x equals 1, so that's going to be, this quadrant and this quadrant, we're going to try to figure out what the graph's doing. And obviously you could check these with a calculator, but the whole point here is to do this by hand to get a pretty quick representation of it. So if we plug in a number close to 1, but larger than 1, like let's say 1.1, okay? And we don't have to, we actually do not care about what the number is. So f of 1.1. All we care about is whether it's positive or negative. So on the right side of 1, if I plug in this number, so I'm going to go to my function that's as the green rectangle, and I'm just going to think about what the sign would be. So 2 times 1.1 minus 1, that's going to give me a positive value. 1.1 plus 4, that's going to give me a positive value. 1.1 plus 2, positive value. 1.1 minus 1 is a positive value. So we're looking at all those things individually, and then we just multiply those together. So positive times a positive divided by a positive times a positive is positive. Okay, so when we're doing this, we're just looking for what the sign would be. And I'm going to erase these because I have to do it a couple times. Okay, so go back. So I know that on the right side of 1, this graph is going to do this. Oop. It will look something like that. Okay, so then on the other side of 1, I actually already know what that's going to do. So what I'll do, I'll explain that in a second. We're going to look at the other asymptote at -2, and so let's choose a number that's close to -2, but on the right side of it. So let's say f of -1.9. So we're going to do the same thing. We're going to go to this function that's in the green rectangle, and we're going to plug these numbers in, but we don't care what the number is, so you don't have to calculate these. We're just looking at whether it would be positive or negative. Okay, so f of -1.9. If I plug that into 2x minus 1, so -1.9 times 2 minus 1, that's going to give me a negative. If I plug in -1.9 to x plus 4, that will give me a positive. If I plug in -1.9 to x plus 2, that's also a positive. And -1.9 minus 1 is a negative. So the question is it positive or negative? Well, negative times positive is negative, divided by positive times negative is negative. So these would both be negative, making the whole thing positive based on those signs. So this would also be positive. Keep doing that same thing. Okay, so this function does something like that. And if you plug in a number less than -1, you'll see that that will also be negative. So the graph does something like that in that middle section. Now, it's really unlikely that this function having an intercept at -4, or an x-intercept at -4. Oh, why did I put -4 out there? -4 is right here. So we already know what the function's doing here. Because if you have this section up here, it's probably going to be the same shape in the other quadrant. So if I plug in a number larger than or more negative than -2 on the left, like -2.1, let's see what that does. So -2.1 times 2 minus 1 is going to be negative. -2.1 plus 4 is positive. -2.1 plus 2 is negative. And -2.1 minus 1 is also negative. So that's going to be a negative divided by a positive, or negative. So if it's negative, that means it goes down towards infinity, like that. So if it's positive, the function goes up near the asymptote. If it's negative, it goes down near the asymptote. So this would be a relatively good representation of this function. Okay, in this example, we're going to go through this one just like we did the last problem. The only difference is that this has a slant asymptote versus any horizontal asymptote. So first thing I want to do is factor this. So the numerator, that factors to x minus 5, x plus 1. And then I'll go ahead and find all the other parts. So the x-intercepts. So again, the x-intercepts are what makes the numerator 0. And in this case, we can see it's x equals 5 and x equals -1. Second, what's the y-intercept? The y-intercept is found by saying p of 0. So p of 0 is 5/3. Third, what's the horizontal asymptote? Well, the degree of the numerator is higher, so there is none. Fourth, what is the vertical asymptote? Well, that's what makes the denominator 0, and in this case, that is x equals 3. Okay, so normally once you get used to these, you can kind of run through all that pretty quickly. And now we have the slant asymptote. What we do with this is just use polynomial long division, and your quotient will be the asymptote. So we're going to say x squared minus 4x minus 5 divided by x minus 3, because that's what our problem says. So then we just go through and do that. So x squared divided by x is x. Multiply, flip the sign. And go through that again. So it's going to be -4x plus 3x. So that's a -x. Drop the -5. Divide. And so this would be -3, so 8. So your slant asymptote is x minus 1, or y equals x minus 1. So let's go ahead and start there when it comes to graphing. So I'm going to graph the line y equals x minus 1 as an asymptote. So that's as a slope of 1, goes through -1. And then we're going to graph the vertical asymptote, which is 3. Okay, so those are our asymptotes. I'm then going to put my points on the graph. So it says x equals 5 is 1, and x equals -1 is 1. And the intercept is 5/3, so somewhere over 1. All right, so those are all the things that we have on our graph, and then we do the asymptote check, which is what we're doing is taking values close to 3, because that's our vertical asymptote. So a number slightly larger, let's say f of 3.1, and we plug that in. So again, we're using this form because it's easiest. We're just looking for the sign. So if I plug in a 3.1 for x minus 5, I get a negative sign. If I plug that into x plus 1, 3.1 plus 1 is positive. And we plug it into the denominator, that's going to also be positive. So this ultimately is going to be negative. I'm going to zoom in, get rid of these, and then do it again. So in this, I'm now going to try f of 2.9 because that's on the left. So again, go up here. 2.9 minus 5 is going to be negative. 2.9 plus 1 is positive. 2.9 minus 3 is negative. So negative times positive divided by negative is positive. So the graph's kind of hinting at this anyway, but you have a function that looks something like that. Okay, in this final example, we're just really looking at in behavior. Now, I'm going to go through the regular parts like I would normally, so I'm going to factor this. And I've already done this division, so if I divide the numerator by denominator, so x cubed minus 2x squared plus 3 divided by x minus 2, I will get x plus 1 times x squared minus 3x plus 3. And that's all over x minus 2. And then we're going to go through all the parts we normally did, so the x-intercepts. X-intercepts are the numbers that make the numerator 0. So one of those is x equals negative 1. Now for the polynomial x squared minus 3x plus 3, if I use the quadratic formula, that gives me complex numbers, so those wouldn't be intercepts on the xy plane, so the only one that works is x minus 1. Second, we're going to check, this is r, so r of 0. This is the y-intercept. So from the r of x in red, we plug that in, and we get a negative 3/2. So that is my y-intercept. I'll write that a little different. So this is the y-intercept. Third, vertical asymptote is x equals 2, so that's what zeroes out the denominator. Horizontal asymptote, the numerator is of higher degree than the denominator, so there is no horizontal asymptote. Okay, so it says in behavior at the top of this one. This does not have a slant asymptote. It has an asymptote that is shaped like a quadratic. Now you don't really have to do a lot of these. This one's just asking about in behavior. It's not even asking you to graph it. But we do have to run this through the polynomial long division and look at what that does. So we would have x cubed minus 2x squared plus 3 divided by x minus 2. And we go through the division. Okay, so these zero out and we get 3. So if I rewrite that as r of x equals x squared plus 3 divided by x minus 2, the in behavior is going to be like x squared. So the in behavior is like x squared, that's all. So that looks like a question mark, that's a period. Okay, so those types of problems, I'm not even sure I put some of those in the assignment this week, but thought I should try show one just in case.